Hi all students. Today we are going to learn how to solve problems involving nuclear energy. But first and foremost, let me ask you a question. What if I told you that the principle of conservation of energy is actually not applicable in all types of situations? Now, you must be wondering, right? Why do I say that, the principle of conservation of energy is not really applicable in all types of situations? For example, in a nuclear decay, we have some mass which is lost, and we call that mass defect. So when this happens, we have to consider the principle of conservation of mass energy, not the conservation of energy only. And then E equal to mc squared. This is what we are going to learn today. Now, let us look at the topic 6.0 nuclear physics and the subtopic 6.2 nuclear physics. And the learning outcome for today is 6.2.3 solve problems involving nuclear energy due to radioactive decay and nuclear reactions. Okay, first and foremost, let's recap on the nuclear fission. Now you have one neutron, okay, which is bombarding a uranium atom. And then at the end of the reaction, you will get barium, krypton, and then 3 neutrons, and also your nuclear energy. What about the nuclear fusion? In nuclear fusion, for example, one deuterium fuses with one tritium, and then you will get one helium and also one neutron, and of course your nuclear energy. Now, what is the difference between nuclear fission and fusion? The biggest difference here is that for fusion, the joining of small nuclei together to give larger ones. Okay, a very small nucleus and another small nucleus, they bind together, okay, they fuse together, they combine together to form a larger nucleus. Well, for the fission, it is the splitting of large nuclei into the smaller ones. For example, you have a very heavy and large uranium atom, and then once it is bombarded by a neutron, and then this will break into some smaller nuclei. For example, the barium, krypton, and then 3 neutrons. Now, let's recall the similarity between nuclear fission and fusion. Can you see the word energy here? And then can you see the word energy here? The similarity between both nuclear fission and fusion is that we will get our nuclear energy at the end of the nuclear reactions. So where does the nuclear energy come from? Okay, so now you have to learn that relationship between mass and energy, because just now when I asked you where does the energy come from, right? The energy actually comes from the mass. Okay, so in other words, we can convert mass into energy, and then the relationship between them is E equal to mc squared. E is energy, m is mass, and then c is the speed of light. Now let us take a look at the mass. Sometimes we call that mass lost, and then sometimes we call that mass difference, but commonly we call that mass defect. So what is mass defect actually? Okay, total mass before fission is this one, and then the total mass after fission is this one, and then the difference between the mass is mass defect. But first and foremost, you might be wondering what is AMU. So I need to introduce the term AMU to you first. Now, AMU is also known as atomic mass unit. Okay, so one atomic mass unit equal to the mass of one carbon-12 atom divided by 12. So, since 1 mole of carbon atoms have a mass of 12 grams, and then 1 mole of atoms have 6.022 times 10 power 23 atoms. By using this formula, you are able to know that 1 AMU is actually equal to 1.66 times 10 power negative 27 kilogram. In other words, AMU is just another unit for mass. Now, please state the mass of one hydrogen atom, one carbon atom, and also one oxygen atom in AMU units. Okay, for example, the hydrogen atom. The hydrogen atom has a mass of 1.0078 AMU. And then one carbon-12 atom has 12 AMU. And then one oxygen-16 atom is 15.999 AMU. So what I want to tell you here is AMU is just another unit that we use to substitute kilogram. Okay, that means in nuclear decay, sometimes we don't love to use kilogram. We love to use AMU as our unit. Okay, so let's come back to this slide. Okay, the total mass before nuclear fission is, 236.05259 AMU. And then the total mass after fission is 235.86653 AMU. Now, the difference in the mass is mass defect. And then this is 0.18606 AMU for this reaction. Now, where does the mass go to? The mass has been converted into energy. When we talk about energy, I also need to introduce you to some common units that we use. For example, we don't really use joule to describe energy, okay, to measure energy. Sometimes we use electron volt. 1 electron volt is equal to 1.602 times 10 power negative 19 joule. Okay, so what I want to tell you here is we might not really use joule to measure energy because sometimes we prefer to use electron volt. Now, let's take a look at the question. The equation below shows radium-226 decaying into radium-222 by emitting alpha particle. Okay, so this is the equation. Given that the mass of 226 radium is 226.54 AMU and 222 radium is 222.018 AMU and the helium particle is 4.003 AMU, please calculate the nuclear energy released. And then I need to tell you that 1 AMU is equal to 1.66 times 10 power negative 27 kilogram and speed of light in vacuum is 3.00 times 10 power 8 meter per second. Okay, so when you need to solve the problem, right? First and foremost, you need to identify the problem first. What does the problem ask you to find? The problem asks you to find the nuclear energy that is released. Now, let us go to the second step. You need to identify all the information given in the question. First and foremost, you know that the mass of this particle is this one. Okay, sorry, the mass of this atom is this one, and then the mass of this atom is this one, the mass of, the alpha particle is this one, and then the speed of light in vacuum is this, and then 1 AMU is equal to 1.66 times 10 power negative 27 kilogram. So you need to jot down all pieces of information given by the question first, before you can go to the step 3. Identify the formula which can be used in this question. In this question, you might be able to use the equation that E equal to mc squared. Okay, because you are given mass in the question and then you need to find out the energy. So the only relationship between energy and mass here is E equal to mc squared. So this is the formula that you can use. Now let's go to the final step. You need to solve the problem. First, you need to find the mass defect, okay, which is the initial mass minus the final mass. Okay, what I mean by the initial mass is the mass before the reaction, and what I mean by the final mass is the total mass of all the particles after the reaction. Okay, so the mass defect here is 0.519 AMU, and then we convert AMU into kilogram. Okay, so 0.519 AMU is equal to 8.6154 times 10 power negative 28 kilogram. Now, once you convert the mass defect in kilogram, what do? You use E equal to mc squared. And then you substitute all the values here, and then you are able to get the nuclear energy released in this reaction. Now, okay, so let's do a short recap on what we have learned today. Today, we have already learned E equal to mc squared. E is the energy, which we also call nuclear energy. And then M is the mass, which is also known as mass defect. And then C is a constant, okay, which is the speed of light in vacuum. And then not to forget the power 2 here, which is the square. Now, units of mass defect can also be in kilogram or in AMU, atomic mass unit. And then units of energy, okay, the nuclear energy, can also be in joules or electron volt. Sometimes you might also be able to use mega electron volt, giga electron volt, kilo electron volt, and so on. Okay, so now, before we end our learning session today, I'd like to give you some questions to test your understanding first. Alright, let's take a look at the problem here. The sun is the source of energy to the earth. This energy is produced by the nuclear fusion in the core of the sun as shown in the following equation. Okay, so you have 2H plus 3H. Okay, this is known as deuterium. This is also known as tritium. Okay, so when a deuterium and a tritium fuse together, you will get your helium and one neutron and also your nuclear energy. Please calculate the nuclear energy released in joules. Okay, so I give you the mass of all the atoms here. Okay, so I want to give you 10 seconds to think about the solution first. Alright, are you done? Let's take a look at the solution. Okay, first and foremost, you go and find out the mass defect. Okay, the mass defect is the total mass before the reaction minus the total mass after the reaction. And then you will get your mass defect in 0.018 AMU. Now, your mass defect is in AMU. So what do? You convert the unit of AMU into kilogram. And then you will know that the mass defect is 2.988 times 10 power negative 29 kilogram. And after you know the mass defect, you proceed to the formula E equal to mc squared. And then you substitute everything so that you can get the nuclear energy which is released. And then the nuclear energy released in this reaction is 2.69 times 10 power negative 12 joule. Okay, so now let us proceed to the final question today. The nucleus of thorium-228 experiences an alpha decay as follows. Okay, so 228 thorium, and then after the reaction, it will give you 224 radium and 42 helium. So please calculate the nuclear energy released in joule. Okay, the mass of 238 thorium is 228.0287 AMU. The mass of 224 radium is 224.0202 AMU, and then the mass of the alpha particle is 4.002603 AMU. Now I tell you that 1 AMU is equal to 1.66 times 10 power negative 27 kilogram, and then the speed of light in vacuum is 3.0 times 10 power 8 meter per second. So what is your solution? I give you 5 seconds to give it a try now. Alright, are you done? So let's take a look at the solution. The nuclear energy is E equal to mc squared. And then the mass defect in this situation is 228.0287 minus 224.0202 plus 4.002603 AMU. And then finally, you will get that your mass defect is 5.897 times 10 power negative 3 AMU. And then you convert the unit of AMU into kilogram. So you know that your mass defect equal to 9.78902 times 10 power negative 30 kilogram. So you use the formula E equal to mc squared, and then you substitute the values so that you get the nuclear energy released in this case is 8.8110 times 10 power negative 13 joule. So I think that's all for today. Thank you very much. Bye bye.